right. Good morning or good afternoon to those of you attending our MOOC course on critical raw material exploration, extraction, and mining. And today I have the pleasure of welcoming Erik Jonsson. Erik is employed at the Geological Survey of Sweden, SGU, as a state geologist, senior geologist, and is also associate researcher with the Smart Exploration Research Center. And Erik today will bring us to what type of geology and mineralization types we have in the Nordic region. So, Erik, I leave it to you then.
Okay, thank you, Alireza, and hi to all. Of course, I will only be able to touch upon these diverse mineralization types of critical raw materials in the Nordic countries. The plan is to give you this general outline. So I'll start with some introductory terminology and some background thinking about critical raw materials and geological processes. And then I will go into the Nordic geology and mineralization types. I will highlight a little bit micro case study, the rare earth elements, the REE, and hopefully finish off with some conclusions. And I don't know how much of questions we will be able to set up. I haven't really cleared this with Alireza, but that's the general plan. And of course, as most of you know that are reasonably well read when it comes to critical raw materials and the EU sense, the EU classification that we work with presently, the latest one is from 2023. We are sitting in this situation where quite a few countries worldwide are absolutely dominating in particularly the mining and the primary production of critical raw materials, but in several cases also particularly the case of China, they're also controlling very much of the processing, so the downstream processes of, for example, rare earth elements, both mining, purification, refining, and downstream production of, for example, magnet materials. And this is, of course, something that started off back in 2009, 2010, with the first crisis between China and Japan. And this was also the set for making the first critical classification list within the EU. What about these metals then? I nicked this fantastic plot of elemental abundances in the upper continental crust. That's the crust that we access absolutely mostly when it comes to mining. These are all figures normalized to 1 million atoms of silicon. And as we can see, we have the most abundant elements, what we can call the rock forming elements in greens here, because they make up the absolute bulk of the crust in the form of rock forming minerals. And then we have, with decreasing abundances, base metals, we have various other metals, we have the rare earth elements in blue, and we have the rarest metals with the lowest abundances, essentially comprise gold and platinum group metals. So a major issue here, obviously, is how do we see that geological processes or combinations of geological processes can upgrade these rather low average abundances? That is ore geology. And this is also the fundament of understanding how and where to look for any mineralization. So looking at some groupings of particular metals, we have, for example, here in yellow, the so-called HFSE, the high field strength elements. We have in greens, the large iron lithophile elements, and what could be called mantle rock forming elements, so more abundant ones in blue. And if we look at this plot with the ionic radius on the x-axis and cation charge on the y-axis, we can see that, for example, a grouping of rare earth elements here straddling the lower edge of the HFSE and going into the LILEs, we see they are relatively off, all of them, all critical metals off from the mantle rock forming elements with fairly large ionic radii and intermediate cationic charges. Additional critical metals, niobium, tantalum, tungsten, zirconium, hafnium, for example, have higher cationic charges, smaller ionic radii, still very much away from overlapping with the mantle rock forming elements. And if we look at the smaller and also larger but lighter elements such as beryllium, lithium, and obscure cesium, they also plot very much outside of the mantle rock forming elements, and hence they are not elements, all of them, that easily go into ordinary minerals, the rock forming minerals, or even the common ore minerals. So we must note here that the majority of critical metals or critical elements are incompatible in most petrological and geological senses. So this means that particular processes are needed in order to concentrate them to mineable amounts. And of course, I will not go through this in any detail. This is just to highlight for all of you out there the complexness of trying to reconstruct geological processes happening in the past. We're looking here at the Fennoscandian Shield, the Nordic countries, where predominant rock types, for example, in Sweden, are between 2,000 and 1,800 million years old. And the work we have to go through is, of course, to reconstruct processes active then, say at 1,900 million years ago, to try to understand how could these processes have acted and interacted to form greater concentrations of such incompatible elements. So, having said those few words as an introduction, let's move into Nordic geology and critical raw material mineralization types. To note, when I finish off, I will be giving you a reference that covers all of this that I'm saying, basically, with regards to Nordic geology and CRM deposits and much more. So for those of you who want to get deeper into this, please download that paper that I will give the reference to as I finish off. So this is the metallogenic area map of the Fennoscandian Shield. This was published in 2012, so it's getting a bit long in the tooth. A next update is planned to be released next year, 2026. High time, you could say. Here you see that in addition to Norway, Sweden, Finland, we also have Russia, northwesternmost Russia, in the form of the Kola Peninsula in there. Of course, our collaboration with the Russians ended with the military invasion of the Ukraine. So this, based on the former Fennoscandian ore deposit database, the FODD map, will not look like this anymore. We now have changed also the name of this working group to the NOD, NODD, for Nordic Ore Deposit Database. We have stopped collaboration with Russia and started collaboration instead with GEOS and thus included Greenland, which is typically in many senses included in the Nordic countries. And of course, this is very relevant since Greenland, the little that is exposed outside of the ice, is really, really rich in mostly unmined mineral deposits. So, looking at this map, why these strange and sometimes even rather weird patterns, these areas for classification of various metals? You can see the legend down there: base metals, ordinary base metals, ferrous metals, special metals, those are mainly the critical ones, and so on. Well, naturally, these areas follow geological boundaries mainly, where we know that we have had at least the kind of processes that have concentrated certain metals, the ones that you see down in the legend. And this means that, of course, any such kind of classification, any starting point for exploration must be based in the knowledge that we have had at one given time in geological evolution the right conditions for concentrating a certain metal or a certain group of metals in each of these areas. Going to a slightly more relaxed map view, this is the one geological map way of showing the Fennoscandian Shield and its cover units, where we have particularly outlined in detail here the Swedish part of the Svekofenian, we have the Karelian and the rest of Finland. And if we want to summarize this rather complex image, including the overthrusted younger units, the sedimentary cover units still being relict in several places, we can sum this up that we have had a very long and complex geological evolution of this part of the world, starting off in the Archean, going into the Proterozoic, and then we have additional components added over time. So the contrasting pressure, temperature, and additional other time conditions have led to a great diversity in rock types. And of course, since that means we have had different styles of rock forming processes, we have also had different styles of potential mineral forming processes. This makes the Fennoscandian Shield in the Nordic countries well comparable to extensively mineralized regions, as we all know, such as Australia, Canada, Brazil, so forth. All of these representing old, complex, geologically very varied continental areas with a very long history of diverse processes. If we look at Norway, the complexness is perhaps not as pronounced in this map of several units that I will not go into the details. I will only highlight one actually, and that is the orange, roughly northeast, southwest, or northeast, west, southwest, trending orange color in the Oslo region. That's the Oslo Rift, where we have several young geological groupings, mainly intrusive rocks that are relevant here. And in the left flank of this, we see actually written out here Fen, which I will come back to. That's a carbonatite complex that is being developed today for critical raw materials, in particular rare earth elements and niobium. If we look at the most recent summary that we made, this was published in 2021, but it's based on essentially 2020 figures and also the 2020 classification of the EU with regards to CRMs. Actually, we have another one underway. We hope to be giving you all interested people an update on this in 2026, so next year also. Here we have all of the present then critical raw materials of the EU listed under commodities here. You can see the mine production column, very sort of highlighting in the sense that we have a great number of zeros in there. So only for a few of these CRMs do we see actual production. Cobalt, graphite, platinum group metals, phosphorus, silicon metal, and titanium. Zeros in the other columns. Of course, this also goes for corresponding zeros in the refinery and smelter production column. Actually, those of you who look a bit more carefully will note that some of these figures are actually higher than the mine production, which of course means that they are operating on imported materials. And that's typically when we look at Norwegian production of silicon metal, made partly from internally mined quartz, but also from quite a lot of imports. That is essentially because they have relatively cheap electric power in Norway. More interesting perhaps then is to move on and to go to known resources. Now compare this column to the known mine production, and we see some great contrasts. And these are just conservative numbers. We have not included uncertain resource numbers here, only the ones where we have relatively good resource calculations available. Note also that I overscored in red the number for scandium because that was actually a miscalculation that was published. And this will be hopefully righted in the next upcoming version of this, courtesy of Nordic Innovation. So you can see we have rather huge amounts of many of these critical raw material resources known. And then, of course, if we go to the great number of right-hand columns, assumed additional resource potential for each and every country here, we see that most are, happily I say, answered with a yes. We do believe or even know that we have additional resource potential for these particular CRMs in the Nordic countries. And this means that we are basically underexplored. And any one of you that have flown over, say, central Sweden and Finland on a clear and sunny day will know how it looks. It's green, with forests, soils, all hiding the geology. Thankfully, we have geophysics that will tell us a lot, but it will not tell us all. And this, of course, means that for some deposit types where we have really good potential of finding them through various combinations of geophysics and perhaps meager observations, we have reasonably good control. Say, for example, deposits characterized by high connectivity, by magnetics, by radiation, and so on. But for the other ones, well, that's another issue. In the case of Sweden, we were actually the only country in this report that said yes to all critical raw materials. It says something about not just our self-confidence, but certainly about the complexity that we know of the geology of Sweden. So if you just look into some of the most important ones of the CRMs with regards to Nordic conditions, Nordic geology, we will see that cobalt, for example, is presently only being mined in Finland. and that's actually the only significant cobalt production in Europe on a whole. Very significant. Typically, all of these deposits, both the unexploited ones, you can see here in pink, as in all of the following maps as well. So where we find potential exploration areas for the particular CRM. But any major cobalt deposit in the Nordics is typically mafic or even ultramafic hosted, with some market exceptions, and one of them is, of course, the so-called black shales. Black shales are typically known from the Phanerozoic, but we also have metamorphosed black shale equivalents. Most well known is Talvivaara, presently known as the Terrafame mine in Finland. You can see that as the red dot in east central Finland, where we have active production of cobalt. We also have a number of quite well-known skarn-hosted deposits, particularly in Bergslagen in south central Sweden. However, these deposits are, with today's terms, today's thinking, all of them rather small. If we look at graphite, industrial mineral and critical raw material, essential for example, production of batteries, essential for the production of graphene and all graphene derivatives. We have a number of belts here, certainly on Greenland, but most distinctly, I would say, we have some extensive belts in Finland and Sweden and going over into Norway. Typically, these are dominated by metasupracrustal rocks, specifically metasedimentary rocks that have been metamorphosed at variable regional conditions. Often lower amphibolite facies, but we can also have some specific deposits with coarser, purer graphite that are remobilized, or even hydrothermal deposits that have been looked and studied upon in Finland, which are today at least deemed as more suitable for high-tech applications. But overall, I would say that the graphite potential of the Nordic countries is really, really quite large. And today, the only production that we see is in Norway, but we are expecting the development of advanced projects in Sweden. We have a former graphite mine in south central Sweden. You can see that Matsmyra Kringel, Kärnkringelgruvan cluster in green, that partly closed mine, partly unexploited deposits. And we also have big projects up in the north. Again, all of them associated with fairly high-grade metamorphosed metasedimentary sequences. When it comes to lithium, the outlook on the map is rather more limited. We have a few belts of essentially lithium, cesium, tantalum enriched granitic pegmatites. That's basically the only known host rock type for lithium deposits in the Fennoscandian and in Greenland. Greenland has no present prospects for lithium, but I wouldn't be surprised if there popped up a few over time. In the Fennoscandian, then, we have relatively little potential in Norway. We have several known provinces in Sweden, including the most recent discovery, Bergby, which is stretched north of Stockholm and the Bergslagen province. You can see that marked with a red star. We haven't included that in tables previously because we still do not have access to any resource figures, but we're hoping that will come out. Notably, in Finland, we have smaller belts, fewer known regions with LCT-type granitic pegmatites, but the green circle there at Rapazar at MS is the most advanced lithium mine project thus far in the Fennoscandian, in the Nordic countries, and indeed one of the more advanced in Northern Europe. We all look with excitement upon the development there, and hope that this will be something that could be followed by, for example, development also of such deposits in Sweden. You should note all that from the LCT type classification comes that tantalum will follow as a potential mineable metal in all of these LCT systems. Niobium will, of course, follow tantalum. They are always occurring together, but niobium is rarely economical in LCT type pegmatites. I will come back to that. We rather find economic deposits of niobium in alkaline systems and carbonatites. Platinum group metals, well, with the exception of relatively large assessed potential exploration areas on Greenland, we have mainly just a few very specific layered mafic intrusions where we have known economic platinum group metal or PGM concentrations. The only mining taking place today is in Finland, in the north, as you can see, specifically in Kevitsa mine. But there are also a number of other layered intrusions with potential up there. In addition to the platinum group metals, these deposits often contain some relevant amounts of other elements, including noble metals such as gold. So these are quite simple to understand and thus also relatively simple to explore for. It's for several reasons quite easy to find those big enough mafic intrusions of what we could call the right age. A majority of these ones in northern Finland are around 2.4 billion years, so formed in a very characteristic setting, just after or during the rifting of the pre-existing Archean continent. So relatively limited system. We have ongoing studies for platinum group metals and have had that for example in Swedish mafic intrusions, but this for nothing that's even near being economical. Rare earth elements I will come back to a little bit, but suffice to say we have a number of deposits on Greenland and in the Fennoscandian. Most notably, I would say that the biggest known so far unmined rare earth element resource is on southern Greenland. There's a cluster down there in the Gardar province in the south. You can see big green markings there. And the biggest of them all that is presently relevant is called Kringlerne. And by itself, even, it's the biggest untapped known REE resource on Earth. Several of the other ones have been cancelled presently because of new regulations from the Greenland government regarding the maximum amount of uranium in mined material. In Sweden, we have ongoing mining of huge apatite iron oxide ores in the north. Those are the red marked active mines at Kirunavaara and Malmberget. And since these are apatite iron oxide ores or Kiruna type deposits, we also have associated fluorapatite with rare earth element contents and secondary minerals, mainly like monazite, like xenotheme, allanite, and so on, hosting yet additional rare earth elements. And most people who are interested in this will know that LKAB, the company running those iron mines, are also developing methods and new parts of deposits in order to be able to hopefully in the near future produce both phosphorus and rare earth elements as byproducts. So overall, I'll come back a little bit to the rare earth elements, but we see a diversity of deposits and relevant grades and tonnages, particularly in Greenland, but outside of Greenland also in Sweden and Norway in particular. I mentioned tantalum when talking about lithium just a wee while ago, and as noted, most tantalum projects coexist with granitic pegmatites, the LCT type granitic pegmatites. Niobium, however, is a completely different story. All of the really big niobium deposits are associated with alkaline intrusions and in particular carbonatite complexes. And this goes both for the Greenland deposits. Again, you can see that Kringlene or Kilavat Alanguat, if you want to say it in local words, is also a huge niobium resource. So it would be rather favorable to be able to extract both rare earth elements, niobium, and even perhaps hafnium and zirconium, as well as some other components while mining such a deposit. Yet it is still untouched outside of pure exploration. When it comes to the Fennoscandian, the main two interesting deposits, I would say, or mineralizations for niobium would be the Fen complex in the Oslo Rift in southern Norway, where it's actually the only past historic niobium mining taking place in the Fennoscandian and in the Nordic countries altogether. The other one is the presently being developed Sokli carbonatite complex, just sitting next to the border to Russia. And it's actually an outlier from the Devonian Kola alkaline province. And that I will touch upon a little bit more in a wee while. Titanium then, well, we have some of the biggest titanium deposits in Europe in the Nordic countries, and most specifically so when it comes to actively mined and advanced projects, we have the biggest ones in Norway. Along the west coast, you can see in the south, Telnes, that is one of the bigger titanium producers in the world, as far as I know. It's definitely biggest in Europe. And typically these deposits on Greenland and in the Fennoscandian are linked to specific mafic intrusive complexes. But we also have particular metamorphogenic deposits in Norway, like Engebøfjellet. And perhaps a little more surprising for these old geological terrains, we also have secondary alluvial deposits of titanium minerals on Greenland. If you look up in the way far northwest, we have the Thule black sands, huge placer deposits with actually several interesting metals and minerals in them. But titanium is their absolutely biggest resource. So when it comes to titanium in the Nordic countries, I would say that we have quite good control of the deposits. We probably know most of them, besides what is under the ice of Greenland. But we also know that a majority, for example, if we look at Sweden and Finland, are presumably might stay sub-economic, whereas the Norwegian deposits obviously are definitely economic in several cases. Finally, I'll round off with saying a few words about vanadium deposits. As you can see in the maps, we have them spread all over along Greenland, coastal regions, as well as in Norway, Sweden, and Finland. Typically, the vanadium is linked to mafic intrusions. again, like titanium, often contained in as solid solution components in magnetites. But in the case of Sweden here, you see this large prospective pink area in west central Sweden, the Caledonian Black Shales. We actually have that combined with small areas in southernmost Sweden, Hörby in Scania. We have black shale hosted vanadium. Quite a controversial type of deposits. Often vanadium is associated with fairly high or increased contents of uranium and several other alloying metals such as nickel, molybdenum. And of course, the low grades on average in black shales means that they can basically only be mined in open pit operations, with the resulting footprint in the local landscape and, I might say, local communities as well. So it's certainly not an uncontroversial resource, but it remains a resource of very large size, actually putting the Nordics in the top 10 of vanadium resources in the world, which is worthwhile mentioning. I'll highlight a little bit on the rare earth element deposits. I like to push for them. They're kind of the origin of the present critical raw material classification, starting off with the China-Japan crisis in 2009, 2010. And they're still as demanded, maybe 4 to 5 times more than they were just 15 years ago. So looking here again at them, the rare earth elements, are they that rare? Well, perhaps not. They're all here in blue. If you ask a chemist, they will also add scandium, but we geologists typically do not add scandium because it has a different ionic radius charge and hence will not follow most of the rare earth elements in most geological processes. So we skip that one. But here in blue, we have them. The top abundances of cerium, lowermost around lutetium, meaning that the abundances, the average abundances of the rare earth elements actually straddle a majority of base metals or very close to them. And actually the rare earth elements are obviously not that rare. Lead is decidedly less common than cerium, and still it forms easily relatively large deposits. Silver, the lower part of the middle here, Ag, is decidedly more rare or less abundant in the average upper continental crust than basically all of the rare earth elements. And still we do not lack silver deposits. So we must end up here with realizing that while we have rare earth elements in low concentrations in basically all rocks, that's why we use them for petrogenetic studies, for example, they do not form mineable deposits as easily as many of the other base, ferrous, and noble metals. Hence, rare earth elements, not that rare. And these are the guys again. Typically, we classify them into these days in light rare earth elements, so the lighter ones of the lanthanoids, lanthanum, cerium, praseodymium, neodymium, and samarium often. And the heavy rare earth elements, the continuation from europium to lutetium plus yttrium, because yttrium will also move and act similarly to the heavy rare earth elements, the heavy lanthanoids in geological processes. And this will govern much of their behavior. We typically see that certain geological processes tend to concentrate the light ones, certain other ones tend to concentrate the heavy rare earth elements. And of course, different host minerals will tend to prefer light or heavy rare earth elements. So just the mineralogy of a deposit will highlight whether we have a concentration of the LREEs or the HREEs. Is that important? Yes, it is. Because today prices of lanthanum and cerium are really low. We have almost overproduction globally of them. Whereas the mid-heavy ones, if we might call them that, starting with praseodymium, neodymium, are increasingly asked for particularly magnet production. And the highest prices overall are paid for some of the heaviest rare earth elements. So actually this has direct economic repercussions for any individual rare earth element deposit. It's worthwhile taking into account. Coming back to this table, I just want to highlight the fact that total known resources of rare earth elements, and note, mine production, 0. Refinery production, 0. That actually goes for the entire Europe when it comes to primary mine production. We still have huge resources. This is close to 36 million tons of metal, total rare earth elements plus yttrium. And this was before LKAB published data on the Per deposit and on Kirunavaara, so we couldn't include them. The big number here is entirely dependent upon the Greenland deposits. When we subtract Greenland, we are down on not double-digit millions, but single-digit millions. Still very significant resources in a European context, and I would say I would be extremely surprised if the first actual functioning primary production mine of rare earth elements in Europe was not in the Nordics. We are seeing lots of development within the rare earth elements and associated metals and minerals in both Sweden and the general Nordic countries. Sockli was not in. We didn't have any updated numbers on Sockli for rare earth elements or niobium by all means, nor hafnium. But we know that there is severe development taking place there. And this is a carbonatite complex. So again, I say we have this diversity of deposit types when it comes to rare earth elements. That's really, really special. Everyone seems to have Europe's largest deposits of rare earth elements. 12th of January 2023, LKAB said, we have Europe's largest deposit of rare earth metals in the Kiruna area. 6th of June 2024, the Norwegians say, we have Europe's largest deposit of rare earth elements at Fen in the western part of the Oslo Rift. Well, be that as it may, we have really good potential deposits of, again, I say diverse character. We have the carbonatite complex at Fen with particular zones that could be viable to mining because of later hydrothermal processes remobilizing rare earth elements internally. And we have parts of the, let's say, Kiruna apatite iron oxide ore system, namely what's now called the Per deposit in the north of this area, where we have relatively high phosphorus and rare earth element contents that are presently being developed. We also have a singular project located at the edge of Lake Vättern in southern Sweden called Norra Kärr. This is something as interesting as a nepheline cyanitic intrusion of agpaitic character, so very high in high field strength elements like zirconium, but also really, really enriched in the rare earth elements. And actually, what's so special with Norra Kärr is the high proportion of the most economically interesting, hence relevant rare earth elements, the heavy ones. So that is something combined with low or very low uranium and thorium contents that makes this into, I would say, a very seemingly attractive prospect for future development. And it has been drilled. The present known published resource from 2021 is at 110 million tons at about half of 8% total rare earth oxides, where heavy rare earth oxides is equal to or higher than the contents of LREO, that is light rare earth oxides. And this deposit is essentially a deformed plug of nepheline syenite rocks, intrusive complex, has been drilled down and the resource is based down to about 200 meters depth. From there and onwards, downwards, it's open. So this is still a relatively conservative figure, I would say. Quite recently, there has been work in Sockli in northeasternmost Finland showing that we actually have relic deep weathered secondary deposits sitting on top of it. That's super interesting and opens up new avenues of thinking for exploration for these deposits, not least since the only viable non-Chinese, non-American rare earth element mine today is Mount Weld in Australia. That's operating on a thick, such weathered carbonatite deposit. The carbonatite itself, the hard rock, unweathered one, is not economic, but the regolith, the soil produced from the weathering, is. So if these kind of deposits have survived, as in the case of Sockli, if we might find other ones like this, it's really, really interesting for rare earth elements, but also for example, niobium, zirconium, hafnium, and a host of other metals and minerals. So there are things out there that we perhaps do not know too much about yet. Really an unexpected deposit subtype, I would say. So to try to finish off a few conclusions, and I'll see whether we can have questions now or later. That will be up to Alireza here. But summing up these major critical raw material deposits, we can see we have this real diversity in the Nordic countries, including Greenland, but absolute most high abundance is, of course, in the well-studied areas in Sweden and Finland. So most Nordic CRM deposits are definitely linked to very specific geological processes, associated rock types of variable ages. I'd say that the rare earth elements are more genetically diversified than a majority of the CRMs otherwise, occurring in very different deposit types that I've tried to touch upon. You will need to go deeper if you want to understand this fully. I will say that no singular method of exploration will catch them all, except perhaps for very detailed field work by very experienced and very lucky geologists. The Nordics are overall underexplored with regards to non-traditional CRMs. We have a long history of mining here, over 1,000 years depending on where you look, but mostly for base metals, ferrous metals, and to some extent noble metals. The non-traditional critical raw materials have not been judged as relevant for much of this time. Unexpected or indeed unknown deposit types are being discovered. What else is out there? We need new, insightful, and creative thinking. We need people who work with new ideas, new models of deposit formation, and new deposit types. And I would like to finish off with saying that the Nordic countries likely represent the most important target region for exploration for critical raw materials within the EU and within Western Europe on the whole. Thank you. And this is the reference to an open access paper covering basically what I've been talking about today. Thank you.
Thank you, Erik.